Hello everyone, welcome back to my channel. My name is Dr. Yogita Bish and this is the fourth video of my video series called Chemical Bonding. In the previous video, we studied about the different concepts that are very important to understand this today's topic. That is, we studied about the formal charges, how to calculate the formal charges, how to identify the stability based on that. There are certain rules with the help of which we can identify that. Then we also check like how to calculate the total number of the valence electron, how to calculate the lone pair, all those things, and we also touch upon the covalency topic. All these topics are very important to understand today's topic. So if you have not gone through this, if you haven't watched those videos, I'll provide the link for the same. I would suggest that you should first watch that video to understand this completely. Okay, so in today's video we will try to understand how to draw the Lewis structure step by step, each and every step. If you follow these steps, I can guarantee you that you will always end up with the right structure, because it is not only governed by the basic formulas like octet formation, but it is also governed by the certain rules like the how stable the structure is based on the formal charges, or like how or under which condition we need to convert the lone pair into the double bond or the triple bond. So we have to keep all these points in our mind. Okay, so let's just begin with that. So these rules are here, you can just note it down, or you can just take the PDF or the picture of these rules, but these rules are very important to get the correct structure of the Lewis structure of different molecule. Alright, so the first rule according to which we can draw the Lewis structure is find the total number of the valence electron. We will be calling it as TVE. It's not something normally we use. It just for the sake of this today's video, I'm calling it TVE. That is the total valence electron, by adding the valence electron of all the atoms. Okay, for example, we talk about water. Okay, so how to calculate the total number of valence electron for water? How can we do that? So this we can do, that is total valence electron, by adding the valence electron of all the atoms. Okay, so I'm talking about the valence electron only. Okay, so we have here hydrogen whose configuration is 1s1. Okay, so its valence electron is 1. Okay, and whereas oxygen, its configuration is 1s2, 2s2, 2p4. Okay, so out of these electron, these two are the valence electron, the one which are present in the highest principal quantum number. Here the highest principal quantum number is 2, and how many electrons are there? 6. So its valence electron is 6. So what will be the total valence electron for water? It will be 1 multiplied by 2, since we have 2 hydrogen, plus 6 electrons of water, that is total 8. So in case of water, total valence electron is 8. Okay, I hope this rule is clear. Secondly, for anions add electrons, for cations subtract electrons from the total valence electron. How to calculate the valence electron of certain molecules where a positive charge is there or the negative charge is there. For example, ammonium ion. Okay, so how can we do that? For ammonium ion, total valence electron would be, for nitrogen, the total valence electron, the configuration of nitrogen is 1s2, 2s2, 2p3. That is, the valence electron is 5 for nitrogen. Plus for hydrogen, it's 1. Since 4 hydrogens are there, therefore 1 multiplied by 4, and plus charge is there. We actually show ammonium like this. We represent like this, right? So plus charge is there. So according to the second rule, if plus charge is there, I have to subtract these number of electron, whatever the charges are there, from the total valence electron. Had it been plus 2, I should have subtracted 2. Okay, so since here only plus 1 is there, I need to subtract 1. So total number of valence electron would be, in case of ammonium, 8. Okay, if negative charge is there, I should have added that. Alright. Third rule, select the central atom. This is the most important one, because most of the students make mistake in here. There are certain rules with the help of which we can find the central atom. Most common one is the one which is present in the least number. Normally 90% chances are there. If a particular atom is present in the least number, then that will be the central atom. So if equal numbers are present, then we go for the least electronegative. Okay, sometimes we give preference to the least electronegative point. So this is also very important. If you have a confusion like which one to choose, you have to look for the electronegativity. Whichever has a lesser electronegativity, that will be your central atom. Apart from that, we also look for the larger size. If the size is larger, then also it can be a central atom. High atomic number. Or another important point is like which want to make the maximum number of bonds. If one atom is readily available to make 3 bonds and other 4 bonds, then definitely we'll go for something which can make 4 bonds. For example, carbon. That will be our central atom. Okay, so keeping in mind these points, let's just choose the central atom in these examples. Okay, so in case of carbon dioxide, the one which is present the least number. So since carbon is present, 1 carbon, 2 oxygens are there. So carbon will be our central atom. In this particular case, carbon will be our central atom. Okay. Of course, out of carbon and oxygen, carbon is the least electronegative. So most of the in most of the cases, we just look for the first or the second condition. In ammonium ion, nitrogen will be our central atom. Okay. Another thing that you need to keep in mind is hydrogen and fluorine are never, or I would say most of the time, are not central atom. In most of the cases, you will see that hydrogen and fluorine are not the central atom. Okay. Then in water, of course, oxygen is the central atom. In nitrate, nitrogen is a central atom. In sulfate, sulfur is a central atom. This nitrous oxide, this is interesting. So here you can see oxygen is present in the lesser number, right? Only 1 oxygen is there and 2 nitrogens there. According to the first condition, oxygen should be our central atom, right? But in this particular case, we will compare the electronegativity. Nitrogen has a lesser electronegativity. That's why in this particular case, one of the nitrogen atom will be our central atom. Okay. So the third point is check the right atom for the central atom. And most of the time, it is the one which is present in the lesser number. Okay. Then the fourth point, it says that like we have seen certain molecule which has a positive charge and also other which have a negative charge, right? So the positive charge always reside on the central atom. When we are drawing the structure, you will realize the central atom has the positive charge, and if there are negative charges are there, then the negative charge, it reside on the corner atom. Okay. I'll explain it with the help of example later on, but as of now, just remember this. Another thing that you need to keep in mind is we have to keep in mind about the common covalency as well. For example, sulfur. You will come across many examples where you will end up making 3 bonds for sulfur, but whereas in sulfur, its covalency 3 is not possible. Normal covalency it shows is 2, 4, 6. So you can remember this. Or there are other conditions also that will not get fulfilled if we make 3 bonds. Then also like it's not hard and fast, like you have to just memorize it. There are formal charges or other condition that will not get fulfilled if you make the 3 bond. But still it's good to remember when you have to answer really quickly or check out of multiple choice question. Okay, sulfur's covalency is not fulfilling. Okay, that cannot be a right answer. Okay, in that case, you can just remember that. Otherwise, if you are drawing a detailed structure, then you don't need this. Okay. This is point number 5th. Okay. Then the next point is join all the atoms to the central atom with the single bonds and calculate the bond pair electron. Okay. So till now what we have done, we have calculated the total valence electron. If there is a positive or negative charge, then we added or subtracted the electron to get the total valence electron. Then we selected the central atom. Then the next step is calculate the total bond pair electron. In case of water, we have selected like oxygen is the central atom, right? So this is how we just draw. Okay, so always remember, in case of the Lewis structure, it never talk about the shape. So this is not the exact shape of water, we all know that, right? I have drawn it linear, but it's not the linear structure. But Lewis structure doesn't talk about the shape, it just talk about like how they are attached. So what we are going to do is, we are going to select the central atom and attach it with the rest of the atoms, okay, by single bond. Okay, and then we are going to calculate the bond pair electron, and the bond pair electron is whatever the single bonds are there, single bonds multiplied by 2. So in this particular case, we have 1 2 single bond, so bond pair electron in this case would be 4. Okay, then this is point number 6. According to this, calculate the lone pair electron with the help of this formula, that is a total valence electron minus bond pair electron. Okay, so in case of water, the lone pair electron would be total valence electron minus bond pair electron. Total valence electron we have already calculated for water, it's 8, right? So lone pair electron would be 8 minus what are the bond pair electron? 4. So water has 4 lone pair electron. Okay, this is not the exact formula for the lone pair electron. I mean, you will get the idea. Okay, there can be 4 lone pair electron, but there are other certain other condition under which these lone pair electron will sometime will be used for making double or triple bond. Okay, and our next point talk about that condition only. This is the point number 7. According to this, check the octet of each and every atom. Since we are talking about the Lewis structure, okay, and the octet formation is the basis of the Lewis structure, right? So according to this, once you have assigned the lone pair, you have attached everything with a single bond. Now what you have to do is, you have to check the octet of each and every atom. For especially for the first, you start with the corner atoms. So the octet of each corner atom should be completely, that means it should have 8 electron in its octet, except for hydrogen, of course it can have maximum 2 electrons, right? And then we look for the octet of central atom. So always remember, this is very important to know, that central atom must have minimum 8 electron. It must have minimum 8 electron, but central atom is allowed to break the octet rule. In what sense? That means it can have more than 8 electron. It cannot have less than 8 electron, but it must have at least 8 electron, and sometimes under certain condition it is allowed to have more than 8 electron. Okay, I'll explain this with some more example. Let us just go through the rest of the rules. Then this is rule number 8. Okay, rule number 8 says, if above number 6 condition, this is 7, sorry, if condition number 7th is not fulfilled, then use the lone pair electron to make the double or the triple bond. Okay, so what does it means? It means we will assign every atom with the lone pair and then check the octet, and if the octet is not completing, then what we are going to do, we are going to convert that lone pair into bond pair, that is into double bond or maybe into triple bond. Okay, I'll explain it with the help of nitrate ion. Yeah, so I need some space for that. Let me just make some space. Okay, so let's just apply all the rule in case of nitrate ion. Okay, so total valence electron, first let's just calculate the total valence electron for nitrogen. Let me just write down the configuration for nitrogen. It is 1s2, 2s2, 2p3. So total valence electron in case of nitrogen is 5. For oxygen it is 1s2, 2s2, 2p4. So valence electron in case of oxygen is 6, right? So the valence electron, total valence electron in this case would be 5 plus 6 into 3, because we have 3 oxygen atom, and then this nitrate ion is represented like this. It's not 3 negative, it is NO3 single negative charge. Okay, so since negative charge is there, according to the second rule, we have to add the negative charge and subtract the positive charge. Okay, so since negative charge is there, that means I have to add that. Okay, so how many total valence electrons are there? 24. Okay, and the second step is check the central atom. So in case of nitrate, the central atom is nitrogen. So what I have to do? I have to just attach nitrogen with 3 oxygen with a single bond. Okay, this is not the shape, just the structure. According to the next rule, we just have to attach the central atom with the corner atom with the help of the single bond, and calculate these single bond and calculate bond pair electron. So this is 2 multiplied by single bonds. So in this particular case, we have 3 single bonds, so it will be 2 into 3, that is 6. Okay, so lone pair electron would be total valence electron minus lone pair electron, bond pair electron. So it will be 24 minus 6, that is 18. Okay, I need more space. So okay, yeah. So now what we have to do is, we have 18 lone pair electrons, so we have to assign it around the oxygen. Okay, so let's just assign that. Okay, 1 2 3 4 5 6, 1 2 3 4 5 6, 1 2 3 4 5 6. Okay, so the next point is check the octet of the corner and then check the octet of the central atom. So let's just check the octet of the corner atom. 1 2 3 4 5 6 7 8. So its octet is complete. Okay, and you can count the lone pair electron also, it's exactly 18. And for this oxygen also it's 8, and for this oxygen also it is 8. But what about this nitrogen? For this nitrogen we have 2 4 6, each bond considered as twice because they are sharing the electron. So 2 4 6, only 6 electrons are there in the central atom, and that is a violation of the rule. Our rule says the central atom must have at least 8 electron, or sometime under special condition more than 8 electron. Okay, so that means this is a wrong structure. Okay, now what is the solution? Under this condition, the next solution is, whatever the lone pair electrons are there, we will use it to convert it into double or triple bond. So what we can do is, we can use this lone pair to make a double bond. Okay, so let's just do that. So in that case, it will look like something like this. Okay, so this oxygen has 6 electron. It has used 2 lone pair electron for the double bond. So that is why it will left with 4 lone pair of electron, and this will have 6, and this will also have 6. Now let's just calculate the octet. This oxygen 1 2 3 4, each single bond considered twice, 5 6 7 8. So its octet is complete. This has already complete octet. This also had a already complete octet. What about this nitrogen? 2 4 5 6 7 8. So now this nitrogen also have a complete octet. Okay, so this is fulfilling the condition. All right, now what about the formal charge? We need to calculate the formal charge also, because we have to assign it has a negative charge. Where should I place this negative charge? Okay, so for that I need to calculate the formal charge on each and every atom. Okay, I have already made a detailed video on the formal charge and how to check the stability. You can check that the previous video. I'll provide the link for that. I'm just giving a glimpse of that. Okay, so this is oxygen first, this is oxygen second, this is third atom, this is fourth atom. Okay, I'm going to calculate the formal charge of each and every atom. Okay, so as per the octet rule, this particular structure seems to be okay. We are just rechecking its stability based on the formal charge. So the formula for formal charge is valence electron minus lone pair electron minus bond pair electron divided by 2. Okay, this is the formula for the formal charge. So let's just calculate it for the first atom, that is oxygen. The oxygen's valence electron, we know that it's 6, minus how many lone pair electrons are there? 1, 2, 3, 4, 5, 6. 6 minus how many bonds are there? One bond is there, one bond is considered twice, so it will be 2 divided by 2. So minus 1. So this particular oxygen has minus 1 charge. Okay, second is also same, so second is also going to have a minus 1 charge. What about third? Third oxygen, how many valence electrons are there in oxygen? It's 6, minus how many lone pairs are there? 4, minus how many bonds are there? 1, 2, that means 4 bond pairs are there, divide by 2. So it has 0 charge. So this has 0 charge. Normally we don't show the 0 charge. So this also, second atom oxygen also has a negative charge. What about the fourth atom, that is nitrogen? The valence electrons in nitrogen is 5, minus, it doesn't have any lone pair, so it's minus 0. How many bonds are there? 1, 2, 3, 4. 4. That means 4 into 2, 8 divided by 2. That means plus 1. Right? So what does it mean? It means it has plus 1 charge. Okay, so this oxygen has minus 1, this also has minus 1, this has plus 1, and this has 0 charge. Okay, so let's just check whether it is fulfilling the condition. The overall charge is negative, and here we have two negative charge and one positive charge. So one positive, one negative will cancel out, so the overall charge would be negative. Okay, so according to the formal charges also, this is fulfilling the condition. That means this is the right structure. Okay, so I hope this was clear. Let me just redraw the structure. Nitrogen, double bond, single bond, 1, 2, 3, 4, no charge. Nitrogen has plus charge, and these oxygen has negative charge. Okay, then the next rule, this is rule number 9. Calculate the formal charge on each atom, and if the condition of formal charge is not fulfilled, then again use lone pair for double bond or triple bond, and also check the most stable structure based on the formal charges. This is formal charge. So the same example I have already explained. So I'll take one more example to show this. Maybe the sulfite ion. Okay, nitrate ion I have already explained. I'll just explain another example, the sulfite ion. Okay, so first for the sulfite ion, it is SO3 negative. First we need to calculate the total valence electron. Okay, so in case of sulfur, the valence electron is 6, plus for oxygen also it is 6, so 3 into 6, and negative charge is there. Just a second, this is sulfite, so it has a 2 negative charge, sorry. So it is 2 negative, so we have to add 2 charges. Okay, So total would be 26. This is the sulfite ion. Okay. Now first what we have to do, we have to check the central atom. So in this particular case, sulfur is the central atom. Okay. So what we are going to do, we are going to draw the single bond attached with each and every sulfur. Okay. And we are going to calculate the bond pair electron. Okay. So this would be 3 into 2, 6. Right. Then what about the lone pair electron? Lone pair electron is total valence electron minus bond pair electron, that is 26 minus 6. So that is 20. Okay. So what we have to do, we have to distribute these 20 electrons in this structure. Okay. So let's just do that. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And we are left with 2 more. So we are going to assign that to the sulfur. Okay. Now let's just calculate the octet and check whether we have drawn the right structure or not. Okay. So here you can see the octet of oxygen is complete. 1, 2, 3, 4, 5, 6, 7, 8. And here also. And here also. What about this sulfur? 1, 2, 3, 4, 5, 6, 7, 8. So this seems to be legit structure, right? But no, this is not a right structure. There are 2 reasons for considering this as a wrong structure. Number 1, the covalency of the sulfur. Okay. And another thing is, it doesn't fulfill the condition of the formal charge. So let's just check the formal charge and check whether we are getting 2 negative or not. Okay. So for that, what we have to do is, we have to just consider 1, 2, 3 and 4. Okay. Since atom 1, 2 and 3 are same, so their formal charges would be 6 minus, how many lone pairs are there? 6 minus bond pair are 1. So 2 divided by 2, minus 1. So each and every oxygen has minus 1 charge, right? Minus 1, minus 1, minus 1, minus 1, minus 1. Okay. What about the fourth one, sulfur? So sulfur has valence electron 6 minus how many lone pair? 2 lone pair, minus how many bond pair? 3. That means 6 divided by 2, 3. So it has plus 1 charge. Right. So this one seems to be plus 1. Okay. So this is one of the structure. So overall it seems to satisfying the condition, but we have another option also. Okay. Another option is, one of the oxygen can convert its lone pair into a double bond, and in that case, let's just check what will be the formal charge. Okay. So let's do that. Sulfur double bond, single bond. Okay. So we will have 1, 2, 3, 4, and here 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and sulfur also has a double lone pair. Okay. So in that case, here the octet is complete. 1, 2, 3, 4, 5, 6, 7, 8. Here also, and for sulfur 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here sulfur has 10 electron, but that's okay, because I have already told you, like, the sulfur or the central atom must have minimum 8 electron, but it is allowed to break the condition of the octet, and it can have more than 8 electron. Okay. The condition is that it try to expand its octet and it will try to remain its maximum covalency. Okay. And that can be explained on the basis of the formal charges as well. Okay. So let's just recalculate the formal charge. So this is first, second, third and fourth. So first and second are same, and we have already calculated it for previously as well. So let's just rewrite it. 6 minus 2 by 2, that is minus 1. So these two have minus 1 charge. This also has minus 1 charge. What about the third one? It will have 6 minus 1, 2, 3, 4 minus 2 to 4 divide by 2. So it will have 0 charge. So this has 0 charge. What about sulfur? Sulfur has 6 minus 2 minus 1, 2, 3, 4, 8 divided by 2, that is 0. So this sulfur has 0 charge. Okay. So we have another structure where this one, where we have 2 oxygen has negative charge, 1 oxygen has 0 charge, and sulfur has also 0 charge. Whereas in the previous case, we had charge on each and every atom. Okay, and as per the stability of the structure based on the formal charges, what a structure will be more stable if minimum number of atoms have the charges. Okay, I have already explained this in the previous video. There are 3 main rules that you need to keep in mind while calculating the better stable structure based on the formal charge. It's not like this first structure that we have drawn is not possible at all. It is possible, but its percentage would be very less. It's not like it's a concept of resonance. Okay, so it's not like it is going to have 100% this structure. Sometime some percentage it can have this structure also, but this particular structure, the one which we drawn first, it has a higher energy and comparatively lesser stability. That is why the percentage of having this structure is less as compared to this one. Okay, and how we compared? We compared it based on the formal charge. According to the formal charge, it will any structure where the least number of atoms have any kind of charge, that will be more stable. So if I consider this as first and this as second, then first structure is less stable as compared to that of the second. Okay, and you will get to know about this with the help of certain rules that I have already explained in the formal charges. Okay, so I hope everything is clear till now. Okay, so let me just take one of the simplest example to get it more clear. Okay, I'll compare water and hydronium ion. Okay, so in case of water, total valence electron would be 1 into 2 plus 6, 8, right? So next step is, this is first step. Second step, central atom. In this case, central atom is oxygen. So I'll just attach with hydrogen. So bond pair electron is 2 into 2, 4. Lone pair electron, it is, the third step is calculate the lone pair electron, that is the total valence electron minus bond pair electron. So it is 8 minus 4. So it has 4 lone pair of electrons. So what I am going to do, I am going to assign these 4 lone pair in the atoms. Okay, so normally what we do, we assign them to the corner, but since this is hydrogen, hydrogen cannot have a lone pair, so I am going to assign these 2 on the central atom. Okay, and now we are going to check the octet. Fourth step is check octet. Okay, so here in case of hydrogen, it can have maximum 2 electrons. So it has 2 electrons. This hydrogen also has 2 electrons. What about oxygen? 1, 2, 3, 4, 5, 6, 7, 8. So its octet is complete. That means this structure seems to be okay. Not the shape, just the structure. Okay. Similarly, the last example, let's say we are talking about hydronium ion. Okay. So in that case, the total valence electron would be 3 into 1 plus 6, and since plus charge is there, minus 1. So that would be 8. Okay. Then the second step is draw the structure. Choose a central atom. Central atom is oxygen. Attach rest of the hydrogen to this. Okay, so bond pair electron would be 2 into 3. 3 single bonds are there, multiplied by 2, that is 6. How about the lone pair electron? So the lone pair electron would be 8 minus 6, that is 2. So what we have to do? We have to assign this lone pair electron to these atoms. So hydrogen cannot have the lone pair. So we will assign this to oxygen. And the last step is check the octet. hydrogen, each and every hydrogen has a complete, not the octet, that is the condition is maximum 2 electrons, so each and every hydrogen has 2 electron. And what about the oxygen? It has 1 2 3 4 5 6 7 8, so its octet is also complete. So this is the structure of the hydronium. Okay, since these two examples were the simple examples, that is why we do not take into account the formal charges. Okay, and of course I have to assign the formal charge also. I have already told you the positive charge reside on the central atom and the negative charge on the corner atom, that is why the positive charge come here. Okay, and we can check the formal charges also, but in simple molecule like this, in case of water or maybe hydronium ion, formal charges doesn't play that much bigger role. But in case of nitrate, nitrite, carbon dioxide, or maybe sulfate, sulfite, it play a very big role. Okay, so in that case what we are going to do, after drawing the structure, we are going to calculate the formal charge of each and every atom and check whether it is satisfying the condition or not. Okay, so I'll end this topic here only, and I'll make another video where I'll take more examples, like in case of sulfate or maybe carbon dioxide, to explain this topic more. Okay, maybe I'll create a short or something, but if you have any doubt regarding this particular topic, this is very important topic, and most of the students find it difficult to understand. So if you have any doubt or any particular molecule you want me to take up, let me know in the comment below. Okay, I'll see you in the next video. Thank you.